Hi, this is Dr. Viv. Let us look at a concrete example of finding work done in a realistic situation. You have a ramp made of wood and a wooden block of mass 1 kg at the top of a ramp initially. The ramp makes an angle of 30 degrees with the floor, and I give a sharp kick to the block. Well, as expected, the block travels down the ramp, and I say that it comes to the stop at the bottom. I also give you the coefficient of kinetic friction, 0.7. I'm asking to find the work done by all the forces acting on the block, which are gravity, normal, friction, the initial speed of the block, as well as my kicking force work. So let's find them all one by one. Now, as always, you start with a free body diagram, although we're not going to solve this problem using Newton's laws. So the free body diagram is drawn mainly for old time's sake and to make sure that we get all the directions right. Now it's coming to a stop, so that means acceleration is going to be up. So let me just, in my usual convention, take the up direction to be positive then. The displacement vector is acting from top to down, so the displacement vector, which I'll indicate with lines alternated with dots, is going to be this vector which I call D. Okay, the velocity vector is down while it's traveling. What about the forces? As you may expect, there are just three forces acting. The normal force, F sub n, the force of gravity, mg, and the force of kinetic friction, which opposes the direction of the velocity, like that. Let's extend the y coordinate. That angle is also theta. The force diagram leads to the force table next. Even though we're not solving the problem using Newton's laws, it's a good idea to keep doing this for practice. Notice that the x component of gravity is negative and the y component is negative as well. The x component comes with a sine and the y component comes with a cosine. The force of friction is positive in this coordinate system. So that's the state of affairs there. Now let's proceed to find the different works. Let's start with gravity. By the definition of the dot product, gravity makes a weird angle with the displacement vector, so I'd rather use a Cartesian definition. It's the force x component times the displacement x component plus the force y component times the displacement y component. We are lucky because displacement is purely x. The displacement vector is acting from a positive value of x to a negative value of x. So the total value of displacement in the x component of the displacement is actually negative L. So I'm going to get fgx, which is negative mg sine theta, times the displacement in the x direction, which is also negative. And so the answer is just mg L sine theta. Now we'll substitute the numbers, and that's the answer. 1 kg, 9.8 meters per second squared. 1 meter, sine 30 degrees. The answer works out to be 4.9 joules. What about the work done by the normal force? Here it might be better to use the polar version of work done by a force, and that is the work done by a force is Fn dot the displacement d. And so the polar way of writing it is Fn times d times cosine of the angle between the two. Cosine of 90 is 0. So we have the answer, which is 0.00 joules. That was easy. The work done by friction requires us to find the friction force. Well, let's first do that. But the force of kinetic friction is mu kinetic times the normal force. So we first need to find the normal force. How do we do that? For the normal force, realize that the block is not flying up the incline. So off the incline, I should say. So sum of forces in the y direction, which is MAY, should be 0. So I add up all the forces in the y column. This is the only place where I actually use the free body diagram and the force table. So I get Fn equals mg cosine theta. Once I have that, I don't look at the free body diagram again. So I have the force of friction, kinetic, is just mu k times mg cosine theta. Now after this point, I am entirely finding just the dot product of the two things. But here, I think it's better for me to still use the polar form, because I know for a fact that the displacement and the force are equal and opposite. Not equal and opposite, are in opposite directions. So let me do that. This is going to be FFK dot D. And that's going to be, if you look at FFK, it's in this direction and D is in this direction. So the angle is cosine of 180 degrees. And cosine 180 is -1, so that's just going to be mu k mg cosine theta from here times L. Let's plug in the numbers. I get -0.7, that's mu k, 1 kg for mass, 9.8 meters per second squared, cosine of 30 degrees times 1 meter. When that is computed, the answer is 5.94 joules. Alright, what about the initial speed of the block? Here we have to use the work kinetic energy theorem. So the work kinetic energy theorem states that the sum of all the works done on the block, this applies after the kick. Okay, if you include my kick, then the sum of all the works is 0, because initially it was not moving and finally it was not moving. But after I kick it, the work kinetic energy theorem, so the works done by all the forces other than my kick, are going to be the final kinetic energy minus the initial kinetic energy. This will give me the initial kinetic energy. Okay. This also tells us how to get the work done by my kick. If you include the moment before the kick, it was not moving. At the end, it was not moving. So the work done by my kick must basically be the sum of all the works done. So all I have to do is find this, and that's also going to be equal to the work done by the kick. But I'll come to that at the end. I'll write that at the end. Well, let me write that right now. This is also equal to W kick. Alright, so let's find out what this is. The sum of all the works, let's do that first. Well, sigma WF I, which is equal to W kick. So I'm answering both parts simultaneously. Well, that's going to be 4.90 minus, negative W kick, I should say, minus 5.94 joules. And so that's going to be 1.04, I believe, negative 1.04. So that tells me the work done by my kick is going to be equal and opposite to that. So that's going to be 1.04 joules. Now let's calculate the change in the kinetic energy. The final kinetic energy is of course 0 because it's not moving at the end of the ramp. The initial kinetic energy is given by the formula 1/2 mv initial squared. So by the work energy theorem, the sum of all the works, which is negative 1.04, must equal kf, which is 0, minus 1/2 mvi squared. Cancelling the negative signs on both sides, I'm going to get vi is equal to the square root of 2 over m times 1.04 joules. It's pretty awkward, but so let's put the values immediately. I'm going to get 2.08. Joules is newtons times meters divided by mass, which is 1 kg. Well, I think I have some extra time, so let me take particular care with the units. Square root of 2.08, whatever that is, times the square root of newtons, which is F equals ma, so newtons is kg meters per second squared, times meters divided by kg. So I lose my kg, and I'm simply left with meters squared per second squared under the square root, so that becomes meters per second. Square root of 2.08 is 1.44 meters per second. Now, if you want to think about the kick in a different way, think about the kick as operating before the problem started. So here's an alternative way of thinking about the kick. Before the problem even started, the work done by me, or the kick, will be equal to the change in the kinetic energy in the sense of giving this initial velocity. So the final kinetic energy is 1/2 mvi squared, because that's the final kinetic energy, final in the sense of after I kick it, and the initial is 0. So that's the reason for the negative sign disappearing. Okay, 1/2 mv squared is in fact equal to 1.04, and so you can think of it as another way of thinking about the work done by the kick. Still better way of thinking about the work done by the kick is what I did there, and that is if you think of the moment when the ball, when I had not even started kicking it, all the way till the end when it's not moving. When I've not even started kicking it, it's not moving. At the end, it's not moving. So the total kinetic energy change is 0. Therefore, the work done by my kick plus all the work done by everything else must equal 0, and that's how I get that equation. So both those viewpoints give you the same answer.